in our previous class, we learned about we learned about the diffraction, especially on XRD, X-ray diffraction. And in the last class, you did the assignment. Okay, in the last class, what we do in class activities, you are basically trying to what we call to deduce the distance between the groove in the CD. You have the CD, so this is what you do in the last class. You have a CD or DVD, and then you know CD and DVD, they have like, for example, like a groove inside it, but you cannot see lah with the naked eye, you cannot see. But inside this you have the groove. Yeah. You have the groove, and then you want to know what is the distance between one groove with each other. Let's say we put D, and then you shine the laser to that, and you use the what we call the equation. What is the equation? N lambda equal to D sin theta. So this equation, they call it also Young double slit equation. So you use this what we call this equation in order to find the distance between each groove in the CD. You cannot see the groove by itself. Even if you put in the normal microscope, it's very hard for you to see it. Okay. So we use XRD, I mean the idea of diffraction, we don't use X-ray, but we use light, we use laser to sort of like deduce the distance between this groove. So basically you use diffraction, and also the interference in order to find the distance. The distance here, the one that you want to see, is basically the D. Okay, so this is what you do in class. And then I ask you to do assignment on the Bragg's law. Okay, your assignment, and then your assignment here. Your assignment. I mean, the only assignment you will have in this course is this. So basically, what I ask you is to find the different, how this differ with the equation that people use normally in X-ray diffraction. So in assignment, I ask you to sort of like look on another equation, which is what we call Bragg's equation, Bragg's law. People call it Bragg's law or Bragg's equation. The Bragg's law, the equation is what? What's the equation for Bragg's law? N lambda equal to D sin theta. It's more or less like a Young double slit equation, but you have two there. So you already explained about this in your assignment, and this you need to this assignment is included in your learning, meaning that I can use whatever you put in the assignment as a material for the quiz, for the midterm, for the final. Okay. So don't just do this assignment for the sake of assignment, because whatever you do in this assignment will be counted as your reading material. Okay, so that's I will not touch about this because you have done it. So Bragg's law normally is used when people work with the XRD. XRD stands for X-ray. What we call X-ray diffraction. But before we go to X-ray diffraction, we know from what we have done in the class and the assignment, and you have done in the assignment, that by simply shining a wave to a slit or to whatever, you can sort of get a pattern, the diffraction pattern, and from that pattern you can sort of like measure the distance between the what we call between the invisible line. Okay. For example, you have this what we call this thing, one single laser, and here I have this what we call diffraction grating. It's like CD, but it's a special, is just specialized for this purpose lah. This diffraction grating here, the one on my right, has 60 lines. What does it mean? Is that, where is my thing? So diffraction grating. Normally people use diffraction grating to show, but I show you with the CD so that you can relate in real life, much easier lah. But typically people use this very specific grating lah. People got grating. What you can see if you have the what we call, if you have the strong enough microscope to see it, inside this thing, you have like a windows. This windows is made of plastic. Inside this plastic, they are lined. They are lined. Okay. On my right, you have 600 lines. 600 lines. And on my left, susahlah pegang banyak benda ni. On my left, you have how much here? There are only hundreds. Okay. So imagine you have 2 diffraction grating, and now you have this. You have 100 lines. Okay. Now I just want to recap. What happened if I shine a laser to this and to this, the same laser to this, what you will see? What the difference? I want to ask you, what's the difference you will see? The same laser, I will shine to both of these separately. What's the difference you will see? Okay, the hint, the thing will be diffract, the laser will be diffract, but what's the difference? The distance. Which one will be, I mean, you will see the diffraction. Diffraction means that you have a distance like inside. Mean that one, instead of 1 point, you have many points. So now you say the distance make a difference. Let's say this is D. So it can be bigger, it can be smaller. So the red or the blue, which one is the bigger? What will happen if I shine? This is 600. This is 600. My left, this is 600. Umi, sini ya. Umi and Azim. Azim, you tak nak tak apalah. Nak. Semayat, come in front. Umi penat. Okay. So if you look, if you both of you, I don't bring the camera, but if you can look at the diffraction grating, they have what we call, what you can see here. What you can see there in Chinese. But it says that 600. Here it says this one. It says 100, right? 100. So you just try to shine on this thing lah. Try to shine on the 600. So this is the what? Okay. So you get something like this. So you get something like this. Okay. So Maya, come here. You stay here. You just replace here the same place. Can you see at the back? Because normally when I look back at my video. When Umi did the thing, I realized that when Umi did with the CD, Umi body sort of like block the what you can see lah. Okay, so this is what Azim see. Can you see? Can you see? You go back at the back. So maybe you can shine from the far. Okay, because okay. Let me open lah, easy. Okay. Okay, shine. Okay, so you can see like that. Okay, Sumayat, can you come here and just replace with this is 600. You block the camera, I think. Okay. So this is 600 for. So Sumayat, come and replace here. Just replace there. So you can see this is what? 100. So you can see 100 like that. Okay. You can see the difference in terms of this lah. So come here. So this 100 put inside that. If not, I forget. I think I won't. I don't know which one is which. Because they are. I need to. Yeah. Normally, because they are. Yeah. Because I don't know whether I put in the right plastic or not, because there are no what we call, there are no imprint here whether it's 600 or 100. So you can double check it using the equation lah, later on I will equation. But normally when you have a small, it will diffract more. So I think this is basically so this, I think, I'm not sure, this is basically 100, I think, and this instead of. But we can double check lah. But now I cannot double check. This is, so this maybe 600. So if you have two things and then you combine together, what you will see is you see a pattern. You see sort of like a pattern there and so on. And you know this make a line something like that. Make a line make something this line. So when you try to put it together, you sort of like what we call get the, let's say I do something like this, and then I put it another one, the blue one, vertically. So you have something like this lah. So this is what you see the pattern just now lah. So from the pattern you can sort of like deduce the what we call the location of the line and so on, the distance and the location. Okay, so this idea can be expanded further. Instead of line, now you have an atom. For example, let's say I have what we call instead of line, you have the atom line perfectly like this, and then you still sort of like have the line lah, the line. Okay, you sort of like have a something like a line here, sort of like here or other way around lah. Okay, so this when you expand the idea of diffraction grating to the atom. Okay, but to see the atom, to see the distance between the atom, between the plane, we call it the plane, the plane. Okay, the plane, the plane, the plane. To measure the distance between the plane of an atom, you need something much smaller than the light. We use green light for here. Green light have the wavelength is around what? Green light. This is so the green light. So the green light, green light. You have the wavelength around 500 something, 550 nanometer. Okay, but the distance between atom, okay, normally in angstrom. In angstrom, the distance between atom normally around 1 to 100 angstrom lah, angstrom. So this is typically the distance between the atom lah, the plane in atom. Okay, depending on the material, different material have different distance. Okay, so different material will give different XRD pattern. Okay. Okay. So we use, instead of using green light or light, we cannot use that. We need to use something that have what we call the wavelength more or less like this. So it turned out that X-ray wavelength more or less, not more or less, they are in this region lah. So that's why we use X-ray. X-ray, because the wavelength of the X-ray, more or less same as the lambda. It's more or less similar to the distance between atom. We learned before that for diffraction to happen pronouncedly, the wavelength of the incident light or incident wave must be more or less the same than the what we call the distance, the gap between what we want to see lah. So it turned out the X-ray have the wavelength more or less equal to the distance between the atom. But in X-ray, it doesn't work exactly like the Young double slit, because Young double slit, this also Young double slit. It's happened, Young double slit happen when you have two opening, and then you have wave come here, and then wave sort of like diffract, and then it interfere with each other. And then you get something, what we call, the bright here, bright here, bright here, bright here, bright here, and so on. So this is what happened in Young double slit. You use XRD, it's not exactly like this, because this you just throw the, what we call, expose the slit to the wave, and the wave diffract and then interfere, and you get the thing. But in an atom, the atom here behaves sort of like the hard ball, more or less like hard ball. So what actually happened is that when you have the wave, let's say you have the wave here, the X-ray coming here, this thing will sort of like reflected, scatter. In other words, we call it scatter lah, elastic scattering. We call it elastic scattering, scattering. And also the second wave also come here, go here, and also something like goes like that, and so on lah. There are many waves. So this thing, the wave here, if let's say the wave sort of like, we know that if the wave is in phase, we call it wave in phase, because here the peak with the peak and the trough with the trough, the peak the same lah. this thing is what we call in phase lah, meaning that this the peak with the peak, this thing with the thing, we know this will give what we call constructive interference lah. So it will go. So when you have something like this, you get something very pronounced like that. So you get constructive interference. So rather than it behave like this, it's more like this atom behave like what we call the hard ball, and it's sort of like scatter the incident X-ray coming in and X-ray coming out. Okay, because when X-ray try to because this, imagine this is your sample lah. This thing is your sample. This thing is your sample. Your sample. For the X-ray to sort of like reflected like this, the sample cannot absorb the X-ray, because if sample absorb the X-ray, then there are no what we call reflection lah. So this we call it scattering lah, because imagine you have the atom here, and then you have the electron here, electron here, and then the X-ray coming in. The X-ray coming in. So what happened is that this electron will scatter here, this will scatter here, this will scatter here. So why it scatter? Because the electron, this X-ray is not enough to excite this electron. Excite the electron meaning that you repel the electron outside or move to another energy level lah. So what happened when the electron is not excited? This thing, the X-ray will come, and then it will sort of like scatter lah, reflect, because conservation of energy lah. If you don't absorb, then you need to re-emit back. So that's why you get this scattering. And when it's scatter, it can be either become like this, meaning that the two X-ray or many X-ray, in reality there are many X-ray, are in phase with each other, and then you get this big constructive interference. So similar idea with this lah. So this, the bright light that you see, is a constructive interference in young double slit. The what I call the no light region here, mean that this is destructive. Destructive interference, and the one that is in black there, this one, this is basically constructive interference. So the same idea, the pattern, how the pattern is generated through the interference. But in X-ray, this atom, they what we call, they sort of like behave like a hard ball, make a plane, and then it will reflect it somehow like that, and then you will get the what we call the D, the distance between the plane, the atom, by using the Bragg's law. And you have done in the assignment why there are two, because you have this thing. So I not discuss that because you have done your assignment. But the idea is that you use X-ray to sort of like to probe this thing. And when you use X-ray, okay, the tool is called XRD. The tool is called XRD. If I show you the what we call the image for the XRD machine, it's like this. XRD machine. Okay, so you can see. Let me go to image. Okay, where is the chanting? Okay, so this is example of XRD machine. We have it in material department, not under our department. But basically, the idea is that you put your sample here, and then this generate the X-ray here, and this will the detector. You can see this is in angle. During when you do perform the experiment, this thing will move. This thing will move in angle like this and go like this. Okay, this thing will move like that. Okay, because why they move? This thing we call it goniometer. Goniometer. What the name? Goniometer. Not important lah. But the idea you need to understand, this will move lah in angle. Why it's move is because in order to get this elastic scattering, where the interference is constructive, there are only specific angle only. Because if you try to go this angle, instead of this angle, you try to shine this angle, then it might not be elastically scattered like this. Maybe if you do this angle, less than this, maybe you just go here, go there, and so on, instead of become like this. So that's why the reason why it's moved in angle is to find where is this constructive interference, because only when you find this constructive interference, only then you can use this formula, and from this formula only then you can find what is D, and from this D only then you can find what is the sort of like, you sort of like reconstruct back the atom location in space. Okay, if the scattering is just haywire like this, then you cannot really use it for the thing lah. Okay, so that's why it's moved to find the angle, of this constructive interference. Okay, when you talk about the XRD, typically people call this field as X-ray crystallography. The XRD is the tool. The field is X-ray crystallography. This is the field, the name of the study on this, how using X-ray to probe the atomic structure. They call it X-ray crystallography. The word here is crystallography. Okay, why crystallography? What is crystal? What is crystal? So Maya, what is crystal? What comes to your mind when I say crystal? Something that is sharp, right? Something is normally when we talk about crystal, we are we imagine in our mind crystal, something like this, something like that, something like this. But at the first place, why people call this crystal? The reason why people call this crystal is because if you see on the facet, we call the edge, this edge we call it facet. If this is crystal, this we call it facet. Okay, this is happen naturally. Normally, in order to get something like this, you need to have human intervention to cut and sort of like that. Because in nature, normally when you see what I call the sand or the rock, normally something like this, right? Something like just there are no structure. But suddenly when people, not suddenly lah, but when you found the crystal have very specific arrangement in such a way that this is very smooth, this very smooth, this facet is very smooth, and this facet is very smooth, and so on. So the reason why it's very smooth is because if you go dig deeper, if you look at the atom here, the atom there is arranged regularly, atomic array like that lah. Only then you can get something like that, smooth edge. The atom, so the term crystal itself, what does it mean? Is basically a solid material. It must be solid lah. Solid material that have regular arrangement of atom. Okay. And only when you have this definite arrangement, only then you can use XRD to probe into. Because let's say the atom is haywire. Instead of like that, the atom is here, whatever lah. If you try to shine the XRD there, this atom will scatter here, this atom will scatter here, this atom will scatter here. So you cannot get this constructive interference. And when you cannot have this constructive interference, you cannot use Bragg's law. And when you cannot use Bragg's law, you cannot find the D. So you cannot sort of like get the structure. Okay, normally the liquid have this structure lah. For example, water molecule. Sometimes the molecule is here, sometimes the molecule is here, and there. So that's why people don't use XRD on water. People cannot see. Okay, so that's one thing. So how then? So in order to perform X-ray, you need to have a crystal first. You need to have the crystal first. So crystal, for example, water. Let's say water. Water by itself is a liquid. Atom, they move here and there. So it's just not stable and also no arrangement. So in order to hold the atom in place, you cool this down, you get the ice. So the ice is basically the crystal of water lah. Normally when you try to cool the water slowly, okay, normally if you want to get a good crystal, you need to cool it slowly. When you cool the thing slowly, the atom that is originally moved here and there, it has time to move slowly and make like sort of like reorient themselves in such a way that you can get as ice lah. Okay, because how water molecule, let's say you have water molecule and then you have water molecule, how they get ice is not just randomly sort of like freeze in what you call freeze in time. It need to rearrange themselves, because for example, you know this will move, will sort of like this O, this ash, you have ash, and you know this is partial negative, this partial positive, this chemistry. Yeah? So in order to sort of like stable, when it become solid, this thing will sort of like make a hydrogen bond with the ash, This is O. The O will make a hydrogen bond with the ash. So it has its own orientation. It cannot just jumbo-mambo go here and there. It must be in specific configuration. So in water, when it's cold, when it's sort of like become ice, it creates a hexagonal pattern. That's why you see the snow get hexagonal and so on lah. If you pass through lah. So that's only happen when you cool it slowly lah. You give time for this molecule to slowly rearrange at their optimal place. Okay, so that's why you get the snow is one of the example of how water, something that is non-crystalline, become crystalline. So you get this hexagonal pattern of the snow and so on. So you basically can make liquid become the crystal. This is how people study what we call the DNA, the protein and so on. Because protein, let's say you have a protein. If I draw you a picture of, not draw lah. If I put you the protein structure, let's say you see the protein structure here. So let's say this protein structure. How people know it's like this? Okay, it's through XRD. But in order to get this, in order for people to know this, they need to have a protein first. And protein normally in your body is so small lah. So if you have only one protein, let's say you have one protein like this, it's not enough to perform the XRD, because you need to have the repeated, what we call the repeated arrangement in order to create this periodic arrangement, so that you can utilize the X-ray scattering to ni lah. So what they do is that they gather a lot of protein, they put in liquid, a lot of same protein, and then this same protein, when it's cooled down, evaporate, it will sort of like a Lego, try to find their match. Mean that they try to sort of like arrange themselves lah, like that, and then you get the crystal lah, you get the solid protein lah. So from this, you put in the what we call in the XRD machine, and then you shine the X-ray, and then you get the ni lah. So the idea for this is, let's say, let me show you some video. So this example of DNA, mana? Kat sini pula. Sorry So this example of DNA. Okay, imagine if you have one DNA, it's not enough. So this basically they try to what we call to mix many DNA together, and then they try, of course, DNA, when you deal with the biological molecule, you need to put it in the water, okay? Because the physiology, not in water, in buffer lah. Because if you put outside the DNA outside like this, they will die, they will shrink. Okay, your protein or your DNA, if you put outside like this, it will dry out, and will dry. When something dry, it will shrink, and when it shrink, then you don't have a structure. So basically, this is what they do. They put in this research they try to sort of like create a cluster of DNA, and because DNA, when they use the same DNA, they try to sort of like DNA will sort of like self-assemble themselves in such a way they got a periodic arrangement. You see, over time, after you got a lot of that, okay, a lot of that. At first, you see there are no structure. At first, it seems like just this one color is one strand of DNA. They combine a lot of DNA. At first, you see it's just like a mess. But when there are a lot, you can see there are a lot. You can start see a structure. You can start see this DNA. You can see there are like a pattern there. So by having this pattern, only then you can use XRD to shine. You sort of like create sort of like the lattice there. Okay, the lattice there. And from that, you can sort of like study under the X-ray lah, X-ray crystallography lah. Okay, so that's why in order to use X-ray, you need to make it crystal first. You have a blood, you want to see the structure in blood. You can know the chemical makeup of the blood by using chemical analysis. But to see the structure of the blood and so on, you cannot use chemical analysis. You need to see it, but you cannot really see under the microscope. Even electron microscope, you cannot see it. Blood, because when you see something into microscope, you need to make it like a solid on something lah. But if you want to sort of like know the structure like this is basically the atom position in space. This you cannot use chemical analysis. Chemical analysis just tell you, okay, this is what, this is carbon, this is what, this is what. But in order to get this structure, you need to use XRD lah. And structure have a lot thing to do with the function. Okay, if let's say this structure instead of like this, it become skewed a little bit, then this protein we call it malfunction lah. Okay, the structure dictate the function. Okay, it's like a lock and key. If you have a key, if you have a lock and the key they have not right groove, like this, if you have key, and then you have a lock like this, and if this one groove is missing, then you cannot open the lock lah, the padlock. So that's what does it mean by structure dictate the function. Okay, so that is basically the X-ray we learn now. We learn about the relationship between Black law, the Young double slit, the idea how to use diffraction and interference in XRD for atom. We learn about the scattering. We learn about the X-ray crystallography, why we need crystal, what is crystal, and how normally people make crystal. Typically they evaporate the water lah. But we will not deal too much on that because it's a very specific field lah. You cannot just simply evaporate the water, because if you evaporate, let's say you have blood, you want to see the structure of blood, you just evaporate the water, then it will shrink. There are methods for that. Typically they use cryopreservation, but we don't deal on that lah. Just to tell you that you need a lot of things, and then and something will evaporate, and then after evaporate, you get a structure like a crystal. You get a crystal lah. So let's see, is there any protein crystal? Protein crystal. The picture of protein crystal. Protein crystal. Okay, so this is how protein crystal look like lah. So after they grow, they got like this. This is very small lah. It's very small. So they put this on the XRD machine, and then they get the value. So this is how they create the crystal lah. From a lot, and then they evaporate. The way how they evaporate, that's another study lah. But that's how they need to make a crystal before they put in the XRD. You can see here the same protein repeated again and again, and then you can see the lattice and so on. Okay, so now that's about the X-ray crystallography. Let me close this first. Wrap this first. Okay. Okay, let me. But now, before we go to the other tools, because this is under XRD, let us how X-ray is produced first. How X-ray is produced at the first time. At the first time. Okay. Because understanding how X-ray is produced in the first time allow you to understand more when we deal with the electron microscopy later on. Okay. Okay. How to produce X-ray? Normally, people have this, the filament, the hot filament, we call it cathode. Cathode. And then you have sort of like target metal. So let's say this is target metal lah. We call this is target metal. Target metal. So this is anode lah, anode. So in order to produce an X-ray, this tungsten or this filament, we call it filament, is heated up. This filament is heated up. It's heated up. When it's heated, this different color lah. When it's heated, something happen. When you hit something very high, you got something. You got something happening. They call it a thermo-ionic emission. What does it mean is that the electron from this will sort of like excited out. They will sort of like excited out. And because this cathode, this anode, a different polarity, this will go here. Okay. So how to create X-ray? You hit the cathode, you hit the filament, whatever, and then if the temperature is right enough, you get this thermo-ionic emission where the electron from the atom from this filament jump out. Okay, and when it jump out, because there are potential difference between cathode and anode, this electron will go to this target metal. Okay, so this is not yet X-ray. This is not yet X-ray. It's just to show that this what we call the electron move from one place to another place. But they are not X-ray yet. It's just moving here and there. X-ray happen when this electron hit this element. Let's say I draw this element, something like this, atom, and then you have the orbit, and then you have the electron inside, electron, whatever electron lah. So now imagine this electron here. I draw in green, coming here. Let's say I put in wave lah, because electron, as we learned before, electron can behave as a wave. Okay. When electron come here, there are many things happen. We learned before, it can be absorbed, it can be scattered, and so on. So for the X-ray here, so this target metal, okay, this target metal, they choose a specific target metal lah in order to produce X-ray. So what will happen when the electron reach this atom thing? Something will happen. This electron carry enough energy to sort of like kick the core electron. This electron, this thing, have enough energy to kick the core electron. Enough energy to kick out core electron. Core electron meaning that the electron at the ni lah, at the low level, at the this first level lah. Normally in X-ray we don't call you learned before like SPDF orbital, right? S orbital, D orbital, and so on. But in X-ray normally they denote a little bit different. They denote it in as a K, JK, M, N, O like that lah. For example, this shell, this one, they call it K. This M, this is N, and so on lah. Okay, so this is just a notation in X-ray lah. So what happened? The electron here has enough energy to kick the electron from the K or the core orbit lah, core shell. We call it core shell lah, K shell, M shell, N shell. So this thing will then kick out. This thing will kick out. Color apa? Let's say red. They will kick out. Okay, they will kick out. Okay, so when this kick out, now this become vacant. No electron more. So we know before that electron, in order to be stable, you need to fill the ground state lah. So what happened? This thing, the electron from the second, so this M shell will go down. And we learned before, when something go down, something coming out, right? Something coming out. So the moment this fall down, to fill in the what we call this, the vacant place here, it will release the X-ray, and when go down, and then the top will go down. It's like a cascade happening. So then it's released X-ray. This X-ray we call it characteristic X-ray. Okay, why characteristic X-ray? Because different material will have different characteristic X-ray lah. Different material will have a different characteristic X-ray, because depending on the how big is the atom and so on. So yeah, so this how X-ray is produced. Okay, so this is one way how to produce X-ray, characteristic X-ray. Okay, that's one thing. But majority, when you try to sort of like expose this target metal with this cathode, this electron coming here, not all become like this. Not all become like this. Not all this thing able to sort of like keep this thing. Some of the electron just pass through, just because in order to kick, it need to just right angle, right place, and so on lah. But some electron just pass through, and so on. There are another way to develop the X-ray is that, let me draw here. Okay, so this one way. Another way is that another electron come here. Imagine this is a new atom, come here, and then suddenly it goes, because it doesn't, what we call, it doesn't kick. It will sort of like deflect a little bit, because remember, the electron is a negative, so you have this repulsion thing. So basically this have, let's say you have the energy goes here, and then because of the repulsion, they sort of like a break. It's like a break fast, and then this is like the another electron just break slow like that. Okay, so it's like a break deflection by breaking. Okay, breaking. So this deflection by breaking, because the energy here and the energy here is not the same, because when you break, you lose the kinetic energy. Kinetic energy is still energy. Okay, and because energy is conserved, there are excess energy there. So that excess energy is what we call the another X-ray lah, another X-ray. This deflection by breaking here, they sort of like this. Let's say this full energy. This is less. Let's say I put here full energy. This is like less energy lah, less energy. So this, because of there are different in kinetic energy, then it give X-ray, another X-ray lah. Another X-ray, they call it apa nama dia? Bremsstrahlung radiation, or X-ray lah, radiation. Bremsstrahlung is, I don't know lah how to pronounce, but this is German. This is a German word. German mean breaking. Bremsstrahlung. Let me Bremsstrahlung. Bremsstrahlung radiation. Okay. So basically you can see here the electron coming here. So it just deflected here. Okay, Bremsstrahlung, they just sort of like reflected. So this make up 80% of the radiation lah. This only 80 or 90%. This just only a few percent only. So when you try to do something like this, you get two type of X-ray. You get this characteristic X-ray, and you get this Bremsstrahlung radiation. Same also X-ray lah. We call it X-ray, another X-ray lah. So just to tell you, there are two things lah that coming out like that. Okay. So this thing, they give sort of like continuous radiation. This give continuous continuous radiation. Okay, this become like a sharp and short radiation. What does it mean by continuous and sharp radiation? If let's say you try, okay, so like this, Bremsstrahlung, you can see it's like continuous only. So continuous radiation, if let's say this is the detector, imagine this is the detector, okay, X-ray detector. So the detector will see for Bremsstrahlung radiation, it's just like this, continuous. It accounts for 80%. But for the characteristic radiation, a peak like that, a sharp peak. So this peak allow you to characterize this is what, because different atoms have different characteristic, the pattern and so on. So you use this. This is how you create the X-ray. When you see the picture before, the SRD picture, SRD machine. Where this one? The X-ray is produced here. The target metal and so on is happen here. Okay. The production of X-rays happen here. So this you give the characteristic and also the Bremsstrahlung here. So this is your sample, and then because of elastic scattering, this thing will what we call exposed to this detector. Okay, this thing, the filament and also target metal is inside here. Both are inside here. Okay, so that is basically the what we call the X-ray diffraction lah. So that's the thing. So when it's come out and hit the sample, depending on the sample, if you have a crystalline sample, you get a very sharp image. Let's say I put SRD crystalline. Crystalline. This thing. So you see the image between SR. So you can see, if you have amorphous material, you get something like this. Okay, you don't have a peak. Okay, if you have something, you make a crystal, nice crystal, you get something peak like this. Okay, peak like that. Okay, yep. So this is the difference between amorphous, and this is what we call the peak here. Is a crystalline lah. The peak here, the higher the peak, what does it mean? When you see this thing, you see something just like that, right? So this, the middle one is the brightest, right? The middle one is the brightest. So the left or right, it become fader and fader. So basically, what actually this shows is that the higher the peak, meaning the brightest part lah, is intensity. Normally, this is a modern one lah. They just give you the spectra. But previously, they use something like this. Something like this. Something like this. So this, the originally is like this lah. Okay. So you can see here, instead of having the peak, you need to interpret this thing. Okay, this is ring, and so on lah. Instead of peak, it's still ring. So sometimes you see a X-ray image, something like this. So you can see this is different. This is what we call the amorphous material. You can see there are no line, as if there are no dot, lah. No dot here. But here you can see a very sharp line, as if there are dot. So here, this you can use to study the what you call the location of atom. But this is difficult lah. Oh, I can use as a laser pointer. So this you can use as what we call the thing. So people want something like this. Okay, people want something like sharp like this, so that they can analyze the thing. The one that like this is just same like this, but they put it in the graph. It's more or less, but it's put it into graph lah. Put into graph. Easy for analysis lah. If not, you need to study this thing, study the different and so on lah. Normally, the modern SRD, you will get this graph lah. You use this machine. the one that have the 2 arms, and then you get this graph straight away. But if you are, these also have their own useful lah. They are also used, but normally modern SRD they just give you this. Some SRD they give you this, but it's for specific purpose only lah. Sometimes you want this, you don't want this, you want this. Okay, so that's about the SRD. That's about the SRD. So now we cover SRD. We're done with the cover SRD. So any question on X-ray diffraction? So X-ray diffraction allow you to locate atom in space. Okay, and then you can create a map of the structure itself. So that is the purpose of SRD. Allow you to deduce the atom in space, and by doing that you create a map where is the atom located, and then you get the structure. And the structure is important because structure dictates the function. As in any molecule in your body, protein structure, if it's malfunction, you don't have a correct structure, then you don't have a correct function lah. So this SRD, we're done with the SRD. We're done with SRD. So I want to enter the electron microscopy. Electron microscopy. So this is a direct method. Electron microscopy is direct method to see. This indirect, you don't see it. You just shine the X-ray. You don't even see the X-ray. You just see the pattern. But electron microscopy, like a normal microscope, allow you to see directly. Okay. Okay, let me padam dulu. Siapa pernah guna electron microscopy? Syaidah? Nisa? Pernah guna? Pernah guna electron microscope? Pernah guna? Kat mana? Hah? Oh, your father lecturer? Huh? Mardi? Oh. Maybe I can make collaboration. Sorry. So, okay. So maybe Nisa can talk about. Anyone else have you used electron microscopy? You have used microscope before, but anyone have experience use electron microscopy? You use electron to see something. Okay. Okay, but before we go to the electron microscope, first let's see what happened. Why people use electron? Okay, why people use electron to probe the sample? Probe the sample. Okay, normally the sample, when you want to see under the microscope, there are 2 types of sample. There are thick sample, there are thin sample. Let's say I separate this into 2. Let's say there are thick sample and there are thin sample. Thin sample. Normally for thick sample, people use what we call scanning electron microscope. Okay, or SEM. For thin sample, people use transmission. Transmission, apa panjangnya? Electron microscope. They call it TEM. Okay, TEM is like your normal microscope, but they just use the electron instead of light. This is more like your normal, more like it's more like the normal microscope, because normal microscope, if you use a normal microscope, if I put this optical microscope, optical microscope, you have used this during your what we call using your lab 1. So in order to use this microscope, as you can see here, you need to put on the slide, and then you need to put a cover slide. So the sample is thin, right? It's not like you can put something big on the and see it. Normally you put slide, and then you put your sample on that thing, and that sample must be very thin lah. If you have thick, then you really, if you try to see a very thick sample under the under the optical microscope, you really don't see anything lah, because the microscope here they use light coming from the bottom. Okay, light coming from the bottom here. So if you are very thick, there are no contrast in what we call darkness. Okay, you see the image. For example, you can see this thing the cell is because this thing is dense. This thing, whatever they are not darker, is less dense. So the idea of optical microscope is that you have the what we call the light coming from the bottom, and then illuminate this thing, and then the magnification is basically is done by the optic lah, the optic part. Okay. So the light, when it hit the dense material, it will not pass through lah. So that's why you can see the nucleus in the whatever is darker. So it's, you basically create a contrast when you see under the optical microscope. The same idea with the TEM lah, but instead of using light, you use the electron. But before we talk about the TEM, let's talk what happened when the electron hit the sample. Okay, because electron, there are things happen. A lot of things happen when electron hit the sample or material. Let's say you have this thing. Let's say you have this sample. Let's say this sample, and then you try to beam the electron. Let's say this sample lah. Let's say this sample. You try to beam the electron. This, let's say this electron beam. Electron beam. Electron beam. What will happen for the thick? I will go for thick first. I will go for the thick sample first. Thick sample. So let's say this is a thick sample. Let's say the thick sample. Let's say the thick sample. What will happen? This electron carry energy, and then when it hit this thing, it will the electron basically hit the atom inside the sample itself. So there are a lot of things happen. So basically, it will create the pear-shaped thing. So this is let me draw first. So this is basically pear-shaped volume, or basically people call it interaction volume. Interaction volume. So this just to show you that how the electron interact with the with the sample itself. Okay. So normally this thing, when you shine the electron to here, it will sort of like goes between 1 to 5 micron depth like that. Okay. So that's it goes down. Electron sample, this is sample. Let's say this sample. This is sample. Okay. So it will create this interaction volume, like a pear shape lah. Okay. So here a lot of things happen. A lot of things happen because electron, we learned before, if we can electron meet another electron, it can create the X-ray also, right? So basically here you can, let's say I draw here. Let me draw in blue lah. Let's say I draw this thing. Let's say I put here this around 1 to 5 micron. Okay, what will happen is that it will give you, we learned before, characteristic X-ray. We learned before it also can give you Bremsstrahlung radiation, and also it can give you also heat. It can also give you a secondary electron. Okay, secondary where it's primary. So normally when you shine the electron beam, this is what we call the primary electron lah. So primary electron meaning that the electron coming from the beam lah. So that, because you might ask, this secondary where it's primary. Primary is this. And also you can have also backscattered electron. And also you can have also the name auger electron. Actually there are many more lah. There are also cathode ray luminescence, plasmon, surface plasmon, and so on. So you can see the one that I want to tell you is that when the electron hit the sample, many things happen. Okay, many things happen. It's not just simply just like that. They have a lot of things because electron will interact to another electron. So we have covered this thing. We have covered the characteristic X-ray. What does it mean by that? We have covered this Bremsstrahlung radiation. Let me cover a few of this. let me cover three things only lah. This, and this. Let me cover the secondary electron, and then auger electron, and then backscattered electron. Okay, let's start with the secondary electron. Okay, secondary electron. What is secondary electron? Okay, so imagine this is the atom, this is the electron shell, whatever the thing, and then you have the electron here. Let's say I put electron in green, in black lah. In black here, electron, 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 whatever electron lah. So you have this nucleus, you have the electron in the shell. Okay, and we learned before, this basically we call it as a K shell. This is L shell. This is M shell, and so on lah. M shell, and so on. Okay, so imagine the electron beam here. The electron beam is, we say, is a primary electron. Okay, goes coming here. So, you know about characteristic X-ray and Bremsstrahlung radiation. This electron also capable to hit the core electron. Okay, because the story of this not finished yet. Okay, this, when you hit the core electron, okay, this electron coming out. Okay, when hit the core electron, this electron, okay, secondary electron. So this electron will coming out. So this is secondary electron. Because previously the classic X-ray is basically when the electron from the second shell go down, right? But this, what happens to the electron that is expelled? This is the expelled electron, the expelled core electron. So basically, this expelled electron, secondary electron, is expelled core electron. Okay, so this is what we call the secondary electron. So people, in SEM, okay, SEM, what does it mean is that they try to collect this secondary electron, because when you hit the material, the secondary electron will be expelled, will go here and there. So imagine they are sort of like the detector here. The detector will detect the secondary electron, and from this you will get the topography, surface morphology of the sample lah, by analyzing this secondary electron. Because it's like you have this something like this, and then your sample, and then you have the what we call the electron beam, and then something expelled coming out. So this secondary electron. So there are what we call detector. So from different what we call different morphology here, different sample morphology here will sort of like give different amount of expulsion of this secondary electron, and from that from the detector will give you the image lah for this thing. So the image, the topography and the surface morphology is basically coming from this secondary electron. So that is secondary electron. It's basically the electron, the core electron that is expelled from the substrate atom lah. So that is secondary electron. Okay. So what is then the we have done the characteristic X-ray, Bremsstrahlung. Okay. Okay. So the auger electron. So now the auger electron. Okay. So now the auger. Okay. So we know before when this is empty. So now this is empty. I use this. Auger lah. Auger electron. The same thing. Like this. Okay. I will redraw this thing. Come here. Let's say I draw the electron here. There are many electron. So you know this thing is expelled. One electron is expelled as a secondary electron. This is primary electron here. Primary electron. So what happened when you expel, as we learned before, they left the empty space here. Empty space there. and then the electron from the higher shell will go down. So the electron from here will go down here lah. Okay, and we know this will create the characteristic X-ray. Okay, this will create characteristic X-ray we learned before. This happens when it goes down, this also will empty also. And then the electron from the next energy level will go down here, and so on. So to the point that the valence electron, let's say you have the valence electron. Let's say this valence electron is basically the electron at the outer. Let's say this valence electron. Okay, so valence electron is the electron at the outermost. Okay, when this happens, they are sort of like create the energy. This fall when it goes down, it create energy as a characteristic X-ray and so on. But it also create excess energy, because when something fall, it's like creating energy lah. It have excess energy. That excess energy is enough. That excess energy, when this cascade of electron coming down, is enough to expel this valence electron out. It expels that excess energy coming from falling down of electron is enough to emit to emit the valence electron out. Okay, because valence electron have very less what we call attraction to the shell, so this very easy to to go out lah. So the excess energy due to this coming down is enough to kick this valence electron out. So this is when it goes out, this is what we call Auger electron. Auger electron. And this Auger electron is characteristic of the sample. You see, it's happened at the surface only. So people use Auger electron to study the surface. In fact, there are tool, they call it AES, Auger Electron Spectroscopy. Okay, so you have this another tool lah, but we don't discuss it. But just for you to let you know that this Auger electron is specific for specific material lah. So different material have a different Auger electron So people can use this Auger electron because it's a valence. People study the surface using Auger electron because at surface is basically the outermost is valence electron. So people use Auger electron to study the surface lah. Surface analysis, doing the surface analysis lah using AES. So that's Auger electron. So we're done with the Auger. Now the backscattered electron. First electron. Okay, backscattered electron. So same idea, not same idea lah, being that the same picture, and then you have electron. They are electrons. So you see this first electron. So you have this electron, the primary electron coming here, and then it just scattered like that. The same the idea when we do the X-ray diffraction, the scattered lah. The scattered. So this they just reflected. They just scatter. That's why the name is backscattered. It's scattered instead of absorbed or instead of kicking out. It just goes here and then go out. So this is backscattered electron. So this backscattered electron is basically it's basically normally the angle is big lah, because it just scatter. The concept is just scatter out. Okay, so this is backscattered electron. So we have done this backscattered electron. Okay, We have learned about characteristic X-ray and so on. This characteristic X-ray, we have studied before. This characteristic X-ray is also specific to each material. For example, different materials have different characteristic X-ray. Sometimes when you use SEM, you typically heard SEM, EDX. So normally when you perform the SEM, sometimes you heard this EDX. EDX come from siapa lupa dah? Energy dispersive. Energy dispersive X-ray. So we learned about X-ray before. Energy dispersive X-ray. So the X-ray we learned there are classic X-ray and Bremsstrahlung radiation. So classic X-ray, as I said, is specific to each material. So meaning that if you use EDX, another method, normally when you do SEM just to see, EDX to analyze. So basically you can use this characteristic X-ray radiation to study the composition of the material. For example, you have this thing, a metal, whatever, you don't know what's inside the metal, you can see the topography, you can see the metal itself under the microscope, but also at the same time, because they are characteristic X-ray, you can also know what is in the metal. Carbon, how many percent, copper, let's say they are copper, how many percent, and so on. So that elemental analysis, this basically elemental analysis is basically utilize this characteristic X-ray lah to the ni lah, to what you call, to study the thing lah. Okay, I just want to show you the picture. Okay, some picture. Okay, so this is a picture. Oh, kat sini. Itulah, siapa suruh tak buat kelas lagi itu? Tak kabut. Okay, so this is basically a picture that normally you see under the SEM lah. Alamak. Okay, the picture. So you can see normally any SEM picture or TEM, you have the scale bar. You know how to, you just take here. So here, take here, 1, 2, 3, 4. So basically this is 40 micrometer. So they must have a scale bar. And also this kilovolt, this is basically the electron beam. You know that to make the electron, you basically hit the filament, and then this is the energy, the electric, how much electric they supply to hit the filament. So, and this is how we did is working distance, no need to know. So this is 1K. This is normally the maximum optical microscope can go, 1K. So you get something like this. Okay. So this is basically a grid, a copper grid. So inside here I put what we call some fiber lah, some fiber there. So that is 1K. So you can see this is basically and 10K. At 10K you multiply 10 times, 10,000 magnification. Okay. This thing is very small lah. This thing, the one that this thing is a copper grid. It's very small, just small, 3 mm. The copper grid here, this one is basically coming from something like this, and the size is 3 mm. 3 mm. So that is under the microscope, 1000 magnification. So this is bigger, and then you go again. So this is 100 magnification. So you see there are change in the scale bar. So I ask you to what we call to watch the video, right? Bionano fundamentals. So I will discuss there about how to study the thing. So I just want to show something. So this when you go to 500,000 magnification, the same thing. This is nano, 100 nanometer. So this is basically around blah blah blah, around 40 nanometer like that. So when you go higher and higher, it's very difficult to get a sharp image. Okay. I want to show you now, in order to sort of like get this image, you need to make it conductive. Another 3 minutes. You need to make it conductive. In order to make the electron go through flow, you need to make it conductive. If not, you will get black and white. Okay, you need to make it conductive. If you don't make it conductive, you get something like this. Okay. If you don't coat means that In order to make conductive, you need to coat sample with something conductive lah, something conductive. Normally people coat with gold, platinum, or chromium. This is gold lah, aurum, gold. This is chromium. Typically, people coat using this. And how to coat, let me show you first before So normally how to coat, let's say this thing, your sample lah. Let's say you put your sample like this. To coat it, you put into something like this. Something like that, you just do like that. And then you put into this, what we call a coating machine lah. Coating machine, you put sample here. And then you see this gold, right? The idea is that there are gold plate on the top here. Gold plate that are top here. And then when you put on the switch, the electron from the gold will hit the sample. Oh, dia gambar iPad ni. Mana gold? Oh, this not this mica. So no, that's basically the gold coater lah. So that's basically the gold coater. So you need to coat it. If you don't coat it, what you see is you see something like this. Mana tadi? You see something like this. Okay, so this is the image when you don't coat the thing. Okay, dark, white and tu, it's not nice lah. You get something like this. That's why you need to coat. And so this when you don't coat lah. But coating last lah. Okay, so you can see this thing here. Here is clean, right? 100K, 100,000 magnification. This also 100K, but you can see it's not clean. The difference between these two is the coating material that I use. This I use gold. So you can see here, if let's say you have 0 magnification to 1 million, 1 million magnification, okay, typically SEM can go to 1 million like that. So if you use aurum, let's say this is 10,000, this is 100,000 magnification. So normally for the gold is good for here only, gold. Meaning that gold particle, so this basically gold particle coated on the fiber. Okay, because gold is big, it's good only for in this magnification also, because gold particle is big. So when you have something like this and then you have particle that is big to coat, then you get something like that lah. Okay, so you get something like this. So you can see the particle of gold there at this thing. So it's not nice lah to do analysis. So this clean because I use chromium. So this gold here. So and then you have a platinum. Is normally can go here until here. So this platinum, and for the chromium you can go here. Chromium. The reason is simple. The chromium is smaller. The chromium particle is smaller. That's why you get nice. The gold particle is big, but this is cheap. This is cheap. Gold, of course, gold is expensive, but actually chromium is more expensive here, like in this case. Okay, gold is cheap, but it's big particle. Chromium is expensive, but it's smaller particle allow you to high resolution. So I think that's it for today. About the tool, we learn about the XRD. We learn also about the SEM.